everybody, thanks for coming. So today we have very special guests. It's Dr. Linder and Dr. Bruce Grossman from UC Berkeley. So and professors will present you energetic cosmic laboratory, which is going to be built here in Kazakhstan. So please welcome.
Thank you all for coming. I'm going to present a dozen or so slides. Bruce is going to present a dozen or so slides. We have plenty of time for questions. We're here to talk some science, to tell you how exciting it is, to tell you how fun it is to work on. And we don't want to just be talking up here and you listening. We want you to interact. And so when we're talking, we want to hear how you think this is exciting science. We want to hear questions from you. We want to hear, wow, I want to work on that, because we are looking for people to work with the Energetic Cosmos Laboratory. So definitely be vocal, be excited. Don't just wait for us to finish, but if you have a question, just speak right up. So we've made the slide so that there's plenty of time to listen to your questions, your comments, your excitement about whatever is going on. So I'm going to talk from a more concept point of view, the theory of what we're doing, and Bruce is going to talk more on the observational point of view. How do you actually look out into the sky, measure these things, and learn about the universe through the data that you get. So I've called this the dark and the very bright universe, because we're talking about the most energetic processes that go on in the universe. And that's why we named the laboratory here the Energetic Cosmos Laboratory. But one of the great discoveries of the last 2 decades is that most of the universe is not very easy to see. When you look out in the night sky, you of course see the stars. If you have very powerful telescopes, you can see distant galaxies full of stars. But the universe is actually filled with dark matter and dark energy, which you cannot directly see from the light. You have to understand the objects in order to figure out how you see them. So that's going to be the first thing that I talk about. How do we possibly know about the universe? It's not something that we can test in the laboratory. We can't do experiments in the sense of we make a universe, then we make a universe with different properties and we compare them. Okay, we are just observing what is out there in the universe. So how can we possibly know what is going on so far away from us? So this sounds almost impossible, but in fact, we do it right here on Earth as well. We sense things remotely. We understand what's happening to an object without being able to touch it, without being able to be there when it's changing. And so one of my favorite analogies is learning about the past climate history of the Earth by looking at tree rings. So we look at a tree that's fallen down or been cut down, and we can see a record of its past growth over the years, from when it was a very young tree as it grew larger and larger. And so we can learn about the way the Earth was in the past, the climate of the Earth, for example, by looking at the tree rings. Was it a very wet year? Was it a very cold year? If it was a very dry year, very cold year, then maybe the tree didn't grow so much. Whereas if it was a very warm and wet year, maybe the tree grew a lot. And so by looking at tree rings, we can basically look at the past history of the climate where that tree was, its local environment. And that's really exactly what we are doing with the universe. We're going to observe objects in the universe, and we're going to learn about the growth of the objects and the growth of the universe as a whole, as the universe expands. And so we look at distant objects, and in order to look at very distant objects, they have to be very bright so that we can detect them. And so we're looking at the most energetic processes in the universe. Dying stars, supernova explosions, where the star basically gives up all of its energy in a fraction of a second. Black holes, matter around black holes, just incredibly energetic processes. And the reason why we're learning about the past history of the universe is because light travels at a finite speed. And so when we see the light from a distant object, we're not seeing the object the way it is now, but we're seeing the way it was in the distant past, when the light first left it, and eventually traveled all the way to us. The more and more distant objects we look at, the further back in the history of the universe that we're seeing. And so we're going to build up this tree ring picture by looking at more and more distant objects and using those to figure out how quickly the universe expanded. So just like here, how quickly the tree grew told us about the conditions around the tree, the nutrients that it got, the weather and so forth. By understanding how fast the universe expands, we learn about the matter and the energy in the universe at different epochs, at different parts in its history. Because the universe didn't always stay the same. Not only is it expanding, but it had different components at different parts in its history. Matter was denser early on. There was more relativistic matter, what astronomers call radiation, which can be both light and very light particles. And so we can look at the proportions of all of those. And so the distances that we measure to the objects, as we measure how those expand with time, then we're looking at the expansion rate of the universe as a whole. The universe isn't static, but it's expanding over time. And that is slowing down and speeding up. As I say, you're learning about the constituents in the universe. And the tools that we use to do this are large ground-based telescopes and also satellite space telescopes, such as the Hubble Space Telescope. And this is a picture from the Hubble Space Telescope. This is called the Hubble Deep Field. And this is actually a very tiny part of the sky. The telescope just stared at that part of the sky for a long time. And yet you find 10,000 galaxies as you look back further and further in just this one picture. So the nearer galaxies look large and they look bright. There's a lot of star formation going on, for example. And then as you go further and further away, you see that galaxies look smaller and dimmer. And then you get these very small, sort of bluish galaxies as you go even back further and further in the universe. And Bruce is going to talk more about the observations. How do we actually design and build telescopes? He'll talk about one that's being built and used here. And again, what do you do with that data once you get it? How do you interpret that data? So as I mentioned, just like you learn about the climate around the tree, you learn about the constituents in the universe, what the universe is made of. And so when we use those supernovae to measure the history of the universe, then we can use the equations that we have. So in particular, we use Einstein's equations, which tells us how does gravity work as we have different types of matter and radiation in it. And the simple version of Einstein's equations as applied to the universe are called the Friedmann equations. And the Friedmann equations are actually very familiar to you, even if you've never studied them, because they're basically Newton's equations. They're basically Newton's second law, the law of conservation of energy, and so forth. So it's not incredibly difficult things to do. It's not like you have to already have your PhD in order to understand a lot of cosmology. If you have a good undergraduate background, if you know Newton's equations well, if you understand conservation of energy, then you can actually understand a lot about the evolution of the universe. So when we use those observations and those equations together, then we put together this pie chart, this ratio of what different types of energy exist today. And again, this changes as you look back in time. And so the amazing thing is the things that we are most familiar with, so the elements of the periodic table, from hydrogen and helium up to the heavier elements, the things that we learn about in all our classes and chemistry classes that we deal with in the laboratory, you can see it's only about 4% of the universe when we measure them. There's other elementary particles, neutrinos. There's particles that have formed into stars. But the two big parts are what I'll call the old new stuff, because people first started talking about this in the 1930s, became very serious about it in the 1970s, and today we've actually measured how much of it there is fairly well. So there's about a quarter of all the energy in the universe is what's called dark matter. And we think that these are elementary particles. Not ones that we've ever seen in the laboratory. There are many experiments that are going on to look for this dark matter, both astrophysically and in laboratory experiments. But it hasn't yet been actually detected the exact particles. We know that it should exist because of the way galaxies, the stars move in galaxies. We need extra gravity, basically, beyond what is visible in order to bind the stars together in the galaxies. And we give the name of dark matter to that. But what I'm most interested in is this new stuff, which we give the name dark energy, because instead of binding objects together in galaxies, giving extra gravity, it actually weakens gravity. It pulls things apart. So matter tries to come together under gravity. This dark energy pulls the universe apart. It makes the expansion of the universe faster. It accelerates it. And so that's very strange. Okay, it's different than what we're used to thinking about, this sort of anti-gravitational force. And so there's a number of experiments going on trying to make these cosmology observations better and trying to really understand much more what's going on. And the amazing thing is that 95% of the universe are these two unknown types that we haven't been able to detect in the laboratory. We can only detect through astrophysics, through cosmology. And so that means the horizons are wide open for students to go out and make great discoveries. Okay, 95% of the universe is still to be discovered, basically. And so that's what we're trying to do here at the Energetic Cosmos Laboratory. We're studying what is this dark energy, what is really pulling the universe apart, accelerating it faster and faster. These are fundamental mysteries. We're not sure where to look for the solution. We just need to get better data. We need to get better ideas, better concepts. To take a step back and take a sort of historical perspective, you can think of it as what's sometimes called the principle of cosmic modesty. Okay? The fact that we can admit that we actually aren't very special. We don't know that much about the universe. So Copernicus phrased this in terms of his principle, that the Earth was not the center of the solar system. That he looked at the motions of the planets, the motions of the sun across the sky, and he said, the data are basically saying that the sun is at the center of the solar system, not the Earth, and the planets go around the sun. And so he moved us in our minds away from being the center of everything, saying, at least for the solar system, we're not at the center. And then this developed further and further. In the early 20th century, people realized that the solar system is not at the center of the galaxy. It's out from the center of the galaxy, about a third of the way toward the outer parts of the galaxy. So not only isn't the Earth the center of the solar system isn't the center of our galaxy. And then they realized throughout the 1920s and more recently that there are just many, many galaxies through the universe, and there's no real way to define a center for this expanding universe. So just like the balloons that you see all over there, if you put a dot on the balloon, you can't say that dot is at the center. As you blow up the balloon, you'll see all parts of the balloon move away from your dot, but if someone else put another dot on the balloon, all parts of the balloon also move away from that dot. There is no unique way to define a center. And so we have to be modest in this way. We can't say we're the center of the universe. The recent discoveries of dark matter and dark energy said that the stuff that makes us up, the stuff in the periodic table that we learn in school, that's not even the typical part of the universe. There's this dark matter, this dark energy, which doesn't make us up. We're made of hydrogen and helium and oxygen and so on and so forth. So we're not even typical of most of the universe. Okay, so again, we have to be modest that the universe isn't just all about us. So the questions that we're trying to answer looking to the future in the Energetic Cosmos Lab are these very paradoxical questions, these very revolutionary questions, such as what is the nature of the quantum vacuum? So in the laboratory, when you have a vessel, when you have a container, and you remove as much air as you can from that, you create a vacuum. You're trying to get rid of all the particles inside that. And there's many laboratories here that work with this vacuum physics, with creating vacuums to study objects in vacuum. In the universe, suppose you remove all the hydrogen and helium and other periodic table of elements. Remember, there's still the dark matter and dark energy there. Suppose you try to somehow remove all the dark matter. You're left with this dark energy, which, when you removed every particle that you can sort of touch, you're still left with this dark energy. And so that suggests we really don't understand exactly what it means to have a quantum vacuum. That nothingness, a vacuum, still seems to have some energy to it. And cosmology and quantum physics somehow have to work this out, and we don't know the answer. The other way of looking at the problem is gravity. That when you look at the solar system, you can predict the motion of the planets in the solar system very well with gravity. You have to actually go beyond Newtonian gravity. You have to use Einstein's theory of general relativity if you want to be very, very precise. Even for satellites orbiting the Earth, if you want to be as precise as you need to be, for example, for GPS, for global positioning system, you need relativity, special relativity, and general relativity. So that's just within our solar system. Then we go out to our galaxy, we go beyond the galaxy to the expanding universe. At each step, you have to test gravity. You can't just say the way gravity works in the laboratory has to be the same as the way gravity works in the solar system as in the universe. You always want to test those principles. And so that's what this part of it is testing through observations. Is the gravity of the expanding universe Einstein's theory of general relativity, or do you need to have someone else revolutionize gravity the way Einstein revolutionized Newtonian gravity? And we don't know the answer, and maybe one of you will come up with a revolutionary idea of how this can be done. To turn a little bit toward the observations that Bruce will talk about, we want to map the universe. Remember, just with the way the tree rings go, we want to map objects further and further away and throughout the universe. So this is, again, a problem that was faced in history before. How do you map things out very precisely? When people travel across the land, on the Silk Road, for example, when they sail the seas, they want to know exactly where they are, so they know when are they going to get to the next town or the next port. Do they have enough food? Do they have enough water? They need to know distances extremely well in this way. And when you travel on the land, well, that's not so difficult. You ask somebody at one town, how far is it to the next town, because they've been there and come back, and so forth. You have landmarks, you can see mountains, and so forth. When you're on the seas, then it's a little harder to figure out exactly where you are, because one direction looks about the same as the other if you're far away from the land. And people realized that they could use the positions of stars to figure out where they are in latitude, how far from the equator or the pole that they are, so the north-south. But east-west was very difficult to do, because to do that, you have to know basically when noon is. You have to know the time extremely accurately. And if you put a clock on a ship, which is rolling back and forth, then the clock doesn't work very well. You're not very accurate in measuring your time. So they could measure north-south distances very well, but they couldn't measure east-west. And so if you're sailing from one continent to another and you want to know when are you going to reach land, you have to know how far you've gone east-west. And so there's this very interesting book on the history of science called Longitude, because you could measure latitude very well, but you needed the clock to measure longitude. And so this says the true story of a lone genius who solved the greatest scientific problem of his time. And that problem was, how do I measure things east-west? How do I map my journey, my universe, in all coordinates, in all directions? And he invented a clock that would work on a ship. And so you could tell the time, you could tell the longitude, and you could map out where you were. And this was back in the 1600s. So today, I'm going to claim we're in a very similar situation, where we can see where an object is on the sky. We can measure it north-south and east-west on the sky, but how far away it is, the distance, that third dimension of space, is very hard for the light to get to you, and the frequency shifts because the universe is expanding. And so if the galaxy emitted some blue light, then it'll be red light by the time it reaches you. And if the galaxy is really far away, it'll become infrared light by the time it reaches you. And so that third dimension, you want to measure the redshifts of the object. So instead of a lone genius, we now have big collaborations doing these experiments, coming up with these ideas and making these observations. But you could argue that it's still one of the greatest scientific problems of our time, at least in cosmology, how to get those measurements very, very well. And Bruce is going to talk about some new technology devices that we're working with here at Energetic Cosmos Lab, which can get vast numbers of these redshifts in sort of one go, instead of having to look object by object. So this instead of a lone genius, this is a particular collaboration that is mapping these redshifts, and instead of a clock, we have all these fiber optics that basically go to a telescope, to a spectrograph, to measure all of these redshifts. So suppose we look very far back in the universe. We observe it to be expanding, which means it used to be smaller, which means all the matter is packed together more tightly, that it was a denser state, and it was a hotter state. And so we can actually see today the leftover glow of that very hot, dense state. So again, this is somewhat familiar to us, in that if we look at a flame, for example, and we see the hottest parts have a different color than the cooler parts, that the wavelength changes as the temperature changes. So today, when we measure it, it's only about 3 degrees above absolute zero, 3 degrees Kelvin. And so the photons, which used to be so energetic, are now down in the microwave region of the spectrum. Okay? And you have to invent detectors that can see into the microwave. So again, the Energetic Cosmos Lab here is working with these microwave detectors, but we're also working with sort of new technology detectors that can also go into the optical and into the near infrared that are just ultra sensitive. Because again, this is so faint, you're looking at such vast distances that you have to be able to pick up this very, very small signal. And so Bruce will mention something about the challenges in working in the laboratory to design these detectors. So when we look at this glow that's left over from the hot early universe, what does it look like? So that's what it looks like. So what is this a picture of? Well, this is a map. So to put it in perspective, you know that if you are trying to make a map of a sphere, of the whole Earth, that it's very hard to put it on a two-dimensional surface like the screen. You have to distort it in some way. And so here's a map of the Earth. It wraps around, so this part here is the same as that part. And you map it into this sort of elliptical shape. That's one of the ways that you can map a globe, a sphere, onto the two-dimensional surface. And that's the same projection that's used here. But when we look at this is the glow from the early universe. The first question we can ask is, well, that's not very exciting. You said you were going to be doing exciting science here. Why is that exciting? Why does it look so dull? It looks the same everywhere. But that's a really exciting observation, that it's the same everywhere. Why should the temperature of the universe be the same in that direction as in that direction from the very, very early universe? So it's the same temperature everywhere because it was so hot and dense that it could come into thermal equilibrium. That any part that was a little hotter than another, that energy would quickly spread itself out over space. And a cooler region would quickly get heated up by the surrounding hotter matter. And so you had this special state of thermal equilibrium. And that again simplifies the equations enormously, such that you can understand, again, without already having your PhD, you can understand a lot of the features of the early universe by using thermal equilibrium. Well, what if we look with even more sensitive detectors? Is it really exactly the same temperature everywhere? So the answer is no. It's 99.999% the same everywhere. But there's this tiny variation of 0.001%. So you needed incredibly sensitive detectors to map out those slight differences in temperature in different directions. And once you take off the 99.999, that's all the same, you're left with this map of hotter and colder spots. And that's the discovery for which Professor Smoot, who's the founder of the Energetic Cosmos Laboratory here, and Professor John Mather at the Space Telescope Science Institute, they together won the 2006 Nobel Prize in Physics for making measurements of this remnant glow and its variations. And what we're looking at with these hotter and colder spots, this is the early universe baby picture. And those hotter and colder spots mean denser and less dense areas of the universe where there's a little bit more energy, a little bit less energy. And that eventually, over the vast sweep of cosmic time, grows into the density fluctuations that form a galaxy here, no galaxy there, a galaxy here, no galaxy there. And so these temperature variations are all related to the structure that we see in the universe now. And that's another thing that ECL is very interested in studying, that pattern of the formation of structure. So to finish up my part, and then Bruce will tell you about the hard stuff, how do you actually make these measurements at this incredible precision. There is a website that we created several years ago called universeadventure.org, which goes through many of these concepts that I've talked about, the expanding universe, dark energy, how do you look back in time by distant observations, how do you use supernovae as distance indicators to tell how much matter, how much radiation there is. And what we tend to do is whenever we visit somewhere in a country speaking a different language, we ask for volunteers to translate parts of the website into the native language so that then the students in that country can learn cosmology as well. And so if people here are interested in translating it into Kazakh or Russian, then that would be great. And so here's just the front page of it, the beginnings of cosmology. People have looked up into the sky and asked, do stars change? Does the universe change? Are there patterns in the way the stars move, collect into galaxies and move in galaxies? How do we learn about the future of the universe? And how do we learn about the past? Where does the universe come from? So please definitely talk to us if you're interested in either the science questions or learning cosmology by going through this website and then translating it as well. So before I turn it over to Bruce, let me ask if there are any questions at the moment.
Well, thank you.
So you said that the universe is like a sphere, but I've heard somewhere that it's flat. So how it's
right? So
could you repeat the question?
Yeah. So we often say the universe is flat, but the analogy I gave was to a balloon, okay, which comes back on itself. It's rounded on itself. So in physics and mathematics, people often use words in a way which isn't exactly the way you use them in normal language. So the flat that you hear about the universe is a property of the space, and Einstein taught us you always have to think of the space and the time together. The space-time are connected. So if the balloon gets large enough and you're only able to look at one little part of it, then it's going to look flat to you, okay? Because the area of the curvature is far beyond what you've been able to see. So imagine that I have a little flashlight and I'm going to shine it at the surface of the balloon. If I'm very close to the balloon, then it only illuminates a tiny part of the balloon, and I say, okay, that looks flat. As I pull the flashlight further and further away, it's going to illuminate more and more of the balloon, and I see, oh, there's starting to be some curvature. And if I'm very far away, I would be able to see a lot of curvature. So that analogy of pulling the flashlight away is basically, as time goes on, I can see more and more of the space. So it may look flat early on, and then later and later, I can actually see the curvature. Today, when we look out and we map everything that's visible, then it looks flat. And maybe it's perfectly flat, or maybe as time goes on and light has more time to propagate to us, we'll start to see some curvature. There's also other reasons. There's actually a mechanism called inflation, which basically says anything that you're going to see is going to be flat. There's a way of actually forcing it to be flat. And that's a very interesting science problem as well.
Thanks.
Sorry, I had a question. Well, I'm interested in Redshift that you talked about. But my question is, well, for example, I look at one star and I want to infer the speed with which the universe is expanding based on the shift in frequency.
Yes.
But then it has like, it does not necessarily move with the speed that the universe is expanding with.
Exactly.
Yes. So how do you solve these kinds of questions?
Right. So that's an excellent question, because there are several things that change the frequency. On Earth, we know there's the Doppler shift. Okay. If you have a car moving by or something that you can hear the sound from the car, changes its frequency. So there's a change in frequency due to an actual velocity, okay, moving through space, basically. Trying to come up with the frequency shift due to not moving through space, but space itself stretching, okay, which we call the cosmic expansion shift, or usually we shorten it, we just call it the redshift. We have to separate that out from these Doppler shifts, from these motions. So there's two ways of doing that. One is, as you look further and further away, the expansion, the stretching part gets much larger than the actual velocity part. And so when you're nearby, they're confused. They're both about the same order of magnitude. You can't really tell the difference. When you're further out, then what's called these peculiar velocities, these Doppler velocities, are just a small change. The other thing is, these Doppler velocities should be random pretty much. So if we look at that star, we'll get an expansion shift and we'll get a Doppler shift. That star, we get the same expansion shift, but we'll get a different Doppler shift because it's going to move in a different direction than that star. So when you average over many, many objects, then the Doppler shifts should basically just cancel out, but the expansion shift should stay there. So it's a statistical argument, basically.
I just wanted to clarify. I think what you were asking before is that it's mapped because the universe, we assume it as a sphere, and flatness refers not to it being flat, right? But actually it's the linearity of coordinates. And you take the Cartesian coordinates x, y, z, and 1 meter here, 1 meter here, 1 meter here, it's all the same. Right? That's what it means to be linear. And non-linear means that they're curving, quite literally, right? Because of gravity or some other things.
Right, so that was the space-time part, but you said it much
too
more
much.
clearly. Yes.
Yeah, so you need to know about it, come to physics degrees, right? The bachelor, master, other stuff.
Good.
And then you work with this guy still.
Any more questions, or shall we? Okay.
I think I read that in terms of the Kobe map that you showed, that the fluctuations, the slight differences, subtle differences in uniformity are different along different axes. I think I said that George Smoot, that was something that he...
That's right. So when you take this data, you then apply all sorts of statistical tools to it. So you can ask, are there as many hot parts as cold parts, for example? You can say, well, what's the average scale? Are there as many small size deviations as large size deviations? So you do basically a Fourier analysis on the map, and then you can be very quantitative in the statistics.
And are there any current theories as to why those differences occur in different directions or in different axes?
So we think that, so again, this is a very early map. It's not a very high resolution map. There have been new satellites that do much higher resolution maps. And the fluctuations do look basically the same in all directions, what's called isotropy. And that you can measure, you can quantify in different ways from the statistical analysis.
And do we know why those initial fluctuations actually occurred, why the universe moved from...
So it depends how many levels of why you ask. So the basic theory, this inflation theory that I mentioned, predicts that you should generate these fluctuations And it predicts certain theories of inflation, predict the power spectrum, the Fourier transform that you should get. And so if you're happy with that as an answer, then yes, we can predict it. But if you keep asking why, well, why that particular inflation? How did inflation originally start? You can just keep asking more and more deep questions of why, and eventually you get to, I don't know. But you should really say, I don't know today, but we do know of ways that we can continue to make observations to, just like we know so much more than we did 20 years ago, 20 years from now, we will hopefully know much, much more about cosmology. And again, you are the people who will be doing it. All right, let's bring Bruce up, and then Bruce is going to, as I say, talk about the hard part of all this.
Okay, so I have lots of cool pictures. In fact, I'm really all about cool pictures. I don't do any of the